Okay, we have discussing about the restricted three body problem in the last lecture. So, we continue with this and we will try to conclude it today. So, in the restricted three body problem, we got three quintics which were described by this general form x to the power 5 a 4 times x to the power 4 plus a 3 times x cube a 2 times x square plus a 1 x plus a 0 equal to 0. So, where the first quintic, this was described by equation number E 1 in lecture number 18, and this described basically the point L 3. The second quintic, this was described by equation number F 1 in lecture number 18, and this was describing the L 2 point, the second Lagrange point. And the third quintic, this was described by equation number G 1 in lecture number 18, and this described the Lagrange point L 1. Okay, now for the Sun Earth system, the distance between the Earth and Sun has already been normalized. So, this normalization in technical language, this is called the whatever the normalization we are representing here, this is basically the use of canonical units. Okay, so, we have used the canonical units where we represented the quantities in such a way that this distance got normalized to 1. So, this whole distance we represented as 1 unit. Okay. Similarly, our the angular velocity that got equal to 1, the mass of these two particles, they were represented as 1 minus mu 1 star and another as mu star. So, this mass was 1 minus mu star and this was mu star. So, the mass also got normalized to 1. Okay. An advantage of using this unit is that it makes the whole representation very simple. And then our L 1 point, it lies somewhere on this side, L 3 point is there, and L 2 point lies somewhere on the right side of this. So, L 2 point is here and L 1 point is lying here. Now, for the Sun Earth system, mu star, which is m 2 here we are taking for this and m 1 we are writing for this. So, m 2 by m 1 plus m 2, and this is the mass of the earth. Okay, so, this becomes, so we have earlier used earlier I have discussed about how much the mass of the sun and the earth is. So, we can use those values. So, sun mass is around 1.989 into 10 to the power 30 kgs, and the earth's mass is around 5.974 into 10 to the power 24 kgs. So, 5.974 into 10 to the power 24 kgs. So, this gives you a value of 3.0035 into 10 to the power minus 6, and this is much smaller than 1. So, once we have got this mu star, then the coefficients A 0, A 1, A 2, A 3, A 4 can be obtained. Because the equations for the these coefficients A0, A1, A2, A3, A4 we have already written. You just need to insert the value of mu star and compute it, and this can be done in MATLAB very easily. Okay, but the MATLAB it does not give you very accurate calculation, unlike if you program in Fortran or C and use double precision there. Okay, so suppose A0 is written as 1 minus 1 plus 3 minus 1 plus 3 mu star minus 3 mu star whole square. So, with this very small value of mu star, which is around 10 to the 3 times 10 to the power minus 6. Okay. So, mu square will almost this will be 10 to the power minus 11 along with this term along with 3, and this term also 10 to the power minus 6. So, this is very small as compared to A 0. So, A 0 can be approximated as this quantity can be approximated as minus 1. Okay. Similarly, A 1 you can find it out. So, after finding these quantities, the solution for the quintics can be obtained using MATLAB. Okay. And this you can do for the checking purpose. It is a very easy to do. What you need to do here is that the quintic equation you need to write in a format where you will indicate a vector which is y. So, y we will write as 1 and then A4, A3, A2, A1 and A0. Okay. So, this is the way of describing a polynomial in MATLAB, and thereafter you use the command roots y. So, this will give you the roots of this polynomial which describes this y. So, the polynomial of the quintics. So, once you get this solution the roots, so you will obtain 5 roots. Out of this one will be positive and rest other will be complex. Okay. So, we reject the complex root and accept only the positive root. Okay. So, for the L3 point, once you solve, so you get x is equal to 1.0, and what is the point x? Point x we have indicated earlier. Point x is the distance of this is suppose this is the barycenter. So, x indicates the distance of the Lagrange point from the barycenter. Now, in this case mu star is very small, okay, and the distance also we have noted earlier that this distance is nothing but from here to here, this is mu star, and the distance from this place to this place, this is 1 minus mu star. So, this is your mu star. So, this is the distance which is x, which gives you the position of the point L3. So, L3 can be obtained by solving this quintic, and that gives you x is equal to 1.0. So, similarly, solving quintic given by equation E1. Okay. Similarly, for L2 you get x is equal to 1.01 and this you obtained from equation F1. And for L1 you get x is equal to 0.99 and this you get from equation G1. Now, the barycenter which we have shown earlier in the figure, here this is the barycenter which is mu star is very small. So, this almost coincides the point B almost coincides with the center of the sun. Okay. So, we can neglect it and show the all the distances from the sun itself. So, the distances, so we can bring B close to this. So, here this is your B, okay, which is very close to the sun, or either you can, because the B it lies inside the sun itself, it is so heavy with respect to the earth. Okay. So, showing B here in this place. So, all the distances can be written here now. This is 1.0 and distance to the L2 point, this is 1.01 and distance to the L1 point, this is 0.99 and therefore, this distance becomes 0.01 and the distance from here to here also this becomes 0.01. So, this quantity, this is nothing but 1 minus mu star. And this is your mu star, which we have taken as 3.0035 into 10 to the power minus 6 and this is nearly equal to 0. Okay. Now, these are the distances in canonical units or the on the normalized scale and this you can expand it to the original scale. So, if you expand it to the original scale, so this will become 0.01, this will be equivalent to 1.5 times 10 to the power 6 kilometers. Because the distance, this is the original distance from here to here, this is distance R12, this is 1.495978 into 10 to the power 8 kilometers, which is nearly equal to 1.5 times 10 to the power 8 kilometers. So, to expand this distance to the original scale, so we need to multiply it 0.01 into 1.5 into 10 to the power 8 and this gives you 1.5 into 10 to the power 6 kilometers, that is 1.5 million miles, million kilometers. So, this we have already discussed many times that last time we have discussed this, that this distance of the L1 and L2, this is around 1.5 million on the left and right of the earth. Okay. So, this distance also this gets to 1.5 into 10 to the power 6 kilometers and this distance of course, this is 1.5 times 10 to the power 8 kilometers. So, this is how your Lagrange points are distributed about the sun earth on a single line. So, on denormalized scale we have 0.01, this is equivalent to 0.01 times 1.5 times 10 to the power 8 equal to 1.5 into 10 to the power 6 kilometers. Okay, once we have done this, so the same kind of treatment can be given to the Earth Moon system. Earth Moon system, and for the Earth Moon system we know the mu star, this is around 0.01 1215. Okay, because of in this case the m2 will be the mass of the moon. So, m2 is nothing but m moon, and which is equal to 7.34 into 10 to the power 22 kgs, and m1 is m earth, which is 5.974 into 10 to the power 24 kgs, and distance between the earth and the moon. So, r12, this is around 3.844 into 10 to the power 5 kilometers. So, using this you can do the same kind of computation and you can get the results. So, last time we have shown it on the figure also how the L1, L2 points are distributed, and L3 and L4 they lie on the circle on which the moon moves. So, now going into the next topic. Okay, now let us go to the Jacobi integral. So, we have already described the 4 points L4, L5, L1, L2 and L3. So, how to find out the Lagrangian point, that is over. Now, we get back to the Jacobi integral, which we obtained for the relative motion by integrating the equation. So, Jacobi integral basically it indicates the energy in some relative sense, not in absolute sense. So, this integral was written as v square equal to x square plus y square plus 2 times 1 minus mu star plus 2 mu star divided by r 2 minus c, and we wrote it in this way, where phi x y z now this describes a equation of a, this is the equation of a surface. So, basically this equation describes the equation describes a surface. Now, if you look into R1, so R1 is nothing but x minus x b1, which is the distance of the mass 1 from the barycenter. So, x b1 square plus y square plus z square under root, and similarly R2 is written as x plus x b1 or r b1, whatever the notation we have used. Okay. So, y square plus z square. So, here is the mass m1 and here is the mass m2, and this was the barycenter. So, this distance we wrote as x b1 and this distance as x b2, and if we put the proper sign here, and in this direction our the synodic positive synodic reference frame is there, and here the y s is positive. Okay. So, therefore, the any point the x y we choose. So, the radius vector from here to the radius from here to the point P, which is at which the mass m3 is lying. So, this we wrote as r1 s, and later on we dropped the notation S and just we wrote it as R 1. Similarly, from here to here this is R 2. So, these R 1 and R 2 are described by these two equations. Okay. Now, we know that V a square, previously we have written V a square is equal to phi minus C, and V a square is a positive quantity. So, it cannot be negative. So, this inequality must be satisfied. So, for V equal to 0, we get the surface of 0 velocity, and this surface is described by phi equal to C. Okay. So, the phi equal to phi x y z equal to C. So, z is coming in picture because of this R 1 and R 2. The x square y square, there is as such in this here whatever we have written. So, z is coming from this place, and if you look into this equation. So, here there is no existence of z here in this place. Okay. So, the x square y square, if we write this as the distance r, okay, so r square becomes x square plus y square. So, x and y are the distances being measured from the barycenter V. Okay. So, this gives you the equation of a surface. Equation of a surface on which the small mass will have 0 velocity. And so, because the V square we are writing as x dot square y dot square plus z dot square. If you refer to this equation, the Jacobi integral that we developed earlier. So, if V equal to 0, so this simply implies if V equal to 0, so this implies x dot equal to y dot equal to z dot equal to 0. Now, this equation that we have written, let us write this equation as equation number 1. Okay. Phi x y z is equal to x square plus y square times plus this quantity. So, this equation number 1 equation 1 is called Hill's limiting surface. Now, by rules of analytical geometry, double points are defined as points where curve crosses itself or a surface cuts itself. Okay, so, double point will exist here in this place. So, you will have two tangents here, one like this, another like this. So, at double points, so phi we have written V square we have written as phi minus c, okay, and this can also be written as 2 u minus c, where u is the quantity x square plus y square divided by 2 plus 1 minus mu star by r 1 plus mu star by r 2. So, these double points will be given by dou u by dou x equal to dou u by dou y equal to dou u by dou z equal to 0. So, this is a standard result from analytical geometry. But from the equation of motion that we developed earlier in the synodic reference frame, we know that x double dot minus 2 y dot is equal to dou u by dou x, y double dot plus 2 x, this is equal to dou u by dou y, and z double dot is equal to dou u by dou z. So, this we can write as equation number 2 1, 2 2, and this is 2 3. Okay. Since the surface that we are defining, so the surface are places where the third mass has 0 velocity. So, this implies x dot equal to y dot equal to z dot equal to 0, that we have already stated. So, from this equation, if we put already at double points, we see that dou u by dou x, dou u by dou y, dou u equal to dou z equal to 0, and from here we get that this is 2 x dot. Okay. So, and from here if we insert the value for y dot and x dot equal to 0. So, if we are inserting this, so similarly we get here x double dot y double dot is equal to z double dot equal to 0. So, this implies this is from equation 2. So, this statement may be stated as the 5 double points L1, L2, L3, L4, L5 we are stated as may be stated here we write it may be stated that at the 5 double points L1, L2, L3, L4 and L5 no resultant force acts on the particle or the small mass. So, this conclusion from where we have got, first we got the 0 velocity surface and thereby we put here x dot y dot equal to 0, and at the double points we put the quantities where the curves they intersect or touch each other. Okay. So, at that point we kept dou u by dou x, dou u by dou y and dou u by dou z equal to 0. So, this quantity became 0 and here all this the first derivative are becoming 0 and therefore, this is implying that there is no resultant force acting on this. And while deriving the quintics, what we did? So, at that time we assumed that in this equation we assumed that there is. So, for deriving the quintics means for finding out the equilibrium points. So, at the equilibrium points we know that there will not be any acceleration. So, we started with that assumption that there is no acceleration. So, we put x double dot y double dot z double dot equal to 0 and also we put x dot y dot z dot equal to 0. So, now we can see that the way we get from the Jacobi integral from this equation and plotting in terms of the Jacobi integral, because we are taking this Jacobi integral here and this we are writing in terms of u, where u phi equal to 2 u. So, and dou u by dou x, dou u by dou y, dou u by dou z equal to 0. So, from this integral we are getting back to getting the results that there are points where there are no acceleration. We do not have to assume that there are the points where the acceleration will be 0. So, this is a very good result and both way it confirms that even if we proceed from the Jacobi integral we get the same result, or either we start from the equation of motion assuming that the quantity x dot double dot and y dot equal to 0. So, still we get the same kind of result. So, therefore, now it becomes very easy to discuss about the Lagrange points and how to develop them. Now, what we have got here the result, one very important thing to state, this is for the circularly restricted, all these results are for circularly restricted 3 body problem. If the two primary masses m1 and m2 they are moving in an elliptical orbit, then no Jacobi integral exists. This you should remember. Now, we can discuss about the Jacobi integral and expand it. So, we have phi equal to x square plus y square plus 2 times 1 minus mu star So, we can discuss the case 1 and this equal to quantity c on the 0 velocity surface. So, case 1 c is large. So, this can happen by x square plus y square, this becomes large, or r1 becomes small, r2 becomes small. In the case of sun and earth, on the normalized scale we know this distance is unity and the barycenter will lie inside the sun itself. So, we can assume that barycenter is lying here itself and then look into the Jacobi integral. So, if x square plus if c is large, so that can happen, say the L1 point it is almost say L3 point is lying here at the same distance, this is distance and this distance is equal. So, we can make a very big circle here in this place like this, and if we take any point on this circle whose coordinate is x and y. Okay, so, you can see that this is R 1 and this is R 2, and barycenter is also lying here. So, R is also lying here in this place itself. Okay, so, R 1 and R 2 they become large here. Okay. If the circle is this distance is unity, this distance is unity. So, we are taking a circle of radius greater than unity. So, the quantity is quite large. So, if the C is large, then this quantity is nearly equal to 1 and this quantity is almost 0. So, this quantity anyhow this is very small and R 1 is large. So, this quantity also becomes small. So, mainly the contribution comes the x square plus y square, this becomes equal to C. So, this describes the equation of a circle. So, C equal to we can write C 0 and this becomes x square plus y square is equal to C 0. Okay, next we can take the case the B case where the R 1 becomes small. Okay, so, if R 1 is becoming small means we are in the neighborhood of the point M 1. So, we can say that now if we are neighborhood of this point. So, now this becomes your R 1 and this becomes your R 2. Here this is your R 2, this is not R 1 and this is R 1 we have taken. So, do the correction here. Okay. So, this is your R 2 and this quantity is your R 1. So, you can see that R 1 R 2 is large, quite large as compared to R 1 and x square y square this is almost equal to R 1. Okay, and this distance is unity. So, therefore, this implies that R 1 will be much less than the unity value. So, if R 1 is much less than the unity value means x square plus y square, this we can neglect, okay, because here now this distance is also x square plus y square under root. Okay, so, this can be neglected and therefore, what we get this 2 times 1 minus mu star divided by R 1 and also R 2 is large. Now, it is around the value of say 1 or little less than 1. So, R 2 being large as compared to R 1 and therefore, mu star by R 1 this can be neglected. So, if you neglect this, so this quantity becomes equal to C 0 and we can write this R 1 equal to C 0 by 2 times 1 minus mu 1 and R 1 you know what it is, this is x minus x b 1 square plus y square plus z square under root is equal to C 0 by 2 times 1 minus mu 0 square. And if you are working in the x y plane, so obviously we will set z equal to 0. So, in x y plane if we are looking for the surface where it cuts the x y plane. So, obviously, there the z will be equal to 0. So, what you get is x minus x b 1. So, x b 1 also in this case becomes equal to 0 because the barycenter almost is coinciding with the primary mass. So, this quantity square plus y square this becomes C 0 by 2 times 1 minus mu star whole square. Okay, so, this again the right hand side this is a constant. Okay, therefore, this becomes also a equation of a circle. So, for a small values of near the small radius, so that is around the point B, you will find that this C equal to C 0 this will be almost this will be describing a circle, and for also very large values of R 1 it will be almost a circle, but for intermediate value it will turn out to be an oblate. So, similarly you can describe for C case where R 2 becomes small, R 2 is small. So, if R 2 is small, then in the same way R 1 and so 1 minus mu star by R 1, this can be neglected, and also x square plus y square. Now, we are working in this range. Okay. So, now x square plus y square is the distance from this point to this point. Okay. So, here say from this point to this point, this is your R 1 and also this is the distance x square plus y square. Okay. So, here x square plus y square, this will be around the unity value or less than that, because this is a quantity. If you go on the right hand side, this will exceed the value of 1. So, if the square value will be around the 1 value, but the quantity once you take the mu star by R 1 and R 1 being mu star by R 2 and R 2 being small. So, this is your radius in this case R 2. So, if R 2 is small, then you will see that this quantity will be quite large than unity. So, the other quantities can be neglected and we work only with mu star R 2. So, if you work with mu star R 2, so mu star by R 2, this will be equal to C 0, 2 mu star times R 2 will be equal to C 0, and this implies R 2 equal to C 0 by 2 mu star, and again this is the equation of a circle. Moreover, one point should be noted that this circle will be of larger radius and this circle will be of a smaller radius. Reason is very obvious, because in the two cases that you are comparing, R 1 is equal to C 0 by 2 times 1 minus mu star and R 2 equal to C 0 by 2 mu star. Okay. So, C 0 in both the cases it is the same, this is large. Okay. This is the equation that we have taken. We have written R 1 is equal to 2 times mu star by C 0. So, we have written just the reverse thing. This is R 1 is equal to 2 times, here we have done the mistake, R 1 equal to 2 times 1 minus mu star divided by C 0. So, this quantity becomes 2 times 1 minus mu star divided by C 0. So, here also we need to give the correction. So, this is 2 times 1 minus mu star divided by C 0. So, here 2 times mu star by R 2 becomes equal to C 2, and therefore, R 2 is equal to C 0 by 2 times 1 minus mu star. R 2 is equal to 2 times mu star by C 0. Okay. So, and R 1 we have written as 2 times 1 minus mu star by C 0. Now, compare these two equations here. C 0 is both in same in the both these cases, okay. but mu star is quite small as compared to 1 minus mu star. In the case of the Sun Earth system, mu star is almost 10 to the power minus 6, it is almost 0. Okay. So, virtually R 2 will be very small as compared to R 1. So, we have not shown in the on the scale here in this figure, but this is circle of a larger radius, then the circle of this one will be very very small. So, the case 1 can be now shown as we have two masses here m 1 and m 2, and this is c equal to c 0, and here also you have c equal to c 0, and then there is a circle of a small radius c equal to c 0, and you will see that inside this the v square becomes negative. So, this region is not permitted. So, either the particle can exist here in this space, either in this space or either outside this. Okay. So, if we decrease further case 2, c is further decreased. So, c equal to let us say c 1 is less than c 0. So, this can happen by R 1 going up, b R 2 also by going up, and c x square plus y square going down. So, that is this shrinks. So, now we can depict this goes up, this goes up, m 1 is here, m 2 is here, and this is c equal to c 1 is less than c 0. And this is your R 1, and from here also you can show this as R 2, or either if the particle is inside this. So, this is the boundary value R 1 and R 2 can be, R 1 will start from here and R 2 will be this value. So, again this region is the prohibited region. Okay, case 3, c further decreased. If you decrease c further, then there will be a stage when these two circles will touch each other. Okay. So, this is the double point that is now developing, and this is your point L 1. Okay. So, the first Lagrange point has developed now. Okay. And again this remains the prohibited region. So, particle can be either inside this or either inside this or on this surface. So, if this region opens up, then particle can move from this space to this space, and so the permissible region is here, here and here. So, as c is further decreased, okay, so c equal to here, in this case also we can write here c is equal to c 2, which will be less than c 1, c equal to c 2 is less than c 1, here also c equal to c 2, which is less than c 1. So, here c equal to c 3, which is less than c 2, and inside then your two curves. Now, this, remember that this we are getting by putting z equal to 0. Okay. The surface, the 0 velocity surface, it cuts the x y plane. So, this is the x s we have plotted here, and y s we plotted downward here. Okay. So, this is whole thing we are showing it in the x y plane. So, now these two circles, they merge together to produce this kind of result. Okay. So, L1 point was here, now the point L2 develops. So, here again you have C equal to C3 which is less than C2. So, now this C is equal to C3 curve, this meets with this curve and then obviously the double point L2 then develops. Similarly, in the next step this will become larger than this and this radius will shrink. So, this is shrinking, okay. This is shrinking, as we have told that this will go down. So, x square plus y square, this is shrinking. So, as it shrinks, so this and this expands, so they will come and merge together here in this place, and this space this will open up here in this place in the next stage. So, case 5, C is further decreased. So, if you decrease further, then we have M1, M2, M1 and M2 present here. Okay, so, the outer circle now it merges with this. This merges with this. So, this area remains prohibited, okay, and this is the Lagrange point L3 which develops here. Here is your L1 and this side here L2 has already developed. So, L2 is lying here in this place, mass is, we can replace the mass inside little bit. So, mass is M2 here and L2 has already developed. So, L2 is opening. So, L2 is here in this place, this has opened up, okay, and this is the prohibited region. The shaded area is the prohibited region. So, the particle can move around this, it can, but it still it cannot go outside because this region is not open, but now it is a possible that particle can go outside even. So, and this is the bounding region. Figures are not very good, but still it depicts the idea, and here the L1 point is there, your L1 point, L2 point is here, and the L1 L3 point has recent, now it has developed. Okay. So, finally, if you decrease the value of case 6, decrease C further, and so by decreasing C further, what you will see that M1, M2, point L2 is here, L1 is here and L3 is lying here in this place. So, and L4 and L5 they are lying somewhere here, which still they have not developed. Okay. So, what happens, the this region it shrinks, okay, and it shrinks into this kind of pattern. Okay. So, this region still remains prohibited, okay, where the L4 and the L5 points are lying inside. Okay. So, as you decrease the value of the C further, so case 7, decrease C further, and then you will see that the M1, M2, this is the point L2, L1, and on this side we have L3. So, L4 and L5 those develop. So, the shaded region now disappears into this point L4 and L5. So, the Lagrange points L4 and Lagrange point L5 finally develops. So, in the case of the Sun Earth system, we have seen that this quantity is one astronomical unit, which is the distance between the Sun and Earth, 10 to the power 8 kilometer. This distance turns out to be 1.5 times 10 to the power 6 kilometers, and this distance turns out to be 1.5 times 10 to the power 6 kilometers. Okay. And for the moon earlier we have already written, and this distance from here to here, this is nothing but your 1.5 into 10 to the power 8 kilometers. which is the distance between the sun and the earth. This is your sun and this is earth. Okay. So, this concludes our discussion, but one final thing is remaining. So, whatever I have discussed now, so this is showing you on the x y plane. Okay. So, this is the surface of 0 velocity where it cuts the x y plane. So, it gives you this kind of picture, and the white portion is the permissible region and the shaded portion is not the permissible region. So, surface of 0 velocity, if you look for that in the x z plane. So, because x is coming, so on the x plane itself the L1 and L2 points are lying. So, the L1, L2 those are visible here, you can see here in this place. This is the point M1, this is the point M2, okay, and therefore, this point is your L1, this point is your L2, okay, and this point is showing your L3 point, and this is the contours in the xz plane. Okay. So, the surface where it cuts the xz plane. So, if you plot it, it will look like this, okay, and it can be developed in the same way as we have done. Okay. And similarly, in the yz plane you can see this, because x is not lying here and the Lagrange points they lie in the x on the x line, and therefore, you see here there is as such no Lagrange points lying present here, because the Lagrange points are the double points where the two surfaces they touch each other, but here there is no touching point available and therefore, no Lagrange point in this case. So, this is in the yz plane. So, thank you very much. We conclude our discussion here and we continue next time with the trajectory transfer. Thank you.